Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're looking at a problem from UNSW concerning thermodynamics, a basic problem, still in the beginning, trying to figure things out. And the problem statement reads 2 kilograms of gas initially at 5 bar, so 5B stands for 5 bar, in 300 Kelvin is compressed in a piston cylinder assembly. During this process, the work done in compressing the gas is 150 kilojoules, and the stored energy of the gas increases by 80 kilojoules. Determine the heat transferred during this process. Is it added or removed from the system? Calculate also the final temperature of the gas if C sub V is 0.312 kilojoules per kilograms per Kelvin. So let's first do a quick analysis on what we have. So 5B stands for 5 bar. 5 bar is the same thing as 500 kilopascals, right? 300 Kelvin, that's good. Whenever we're dealing with our specific heats, we want to be sure that we're dealing with Kelvin because they are dealing with Kelvin. We have a piston cylinder device, so we expect this thing to be able to move and stay where it is with the outside pressure during this process to work. So we're putting 150 kilojoules and we're storing 80 kilojoules. So what does this mean? If the energy of the gas increases by 80 kilojoules, we're seeing that the delta U is changing by 80 kilojoules, right? So the final minus the initial internal energy is 80 kilojoules. So we are to find the heat transfer during the process. So they want the heat, so they want Q, right? Q, and to tell whether it's entering or leaving the process, and also to calculate the final temperature. So let's draw real quick what we have. Let me draw my piston cylinder device here. We have, so this is my piston cylinder device. We have a gas, right? Yeah, just a gas. We don't know which gas this is, so just put gas here. And we know there's 2 kilograms of it. 2 kilograms of this gas. And what we're doing is we're compressing, right? So what we're doing is we're applying a force over this area. So we're applying some force this way to compress it. So what we expect is that after we compress it, because this piston can move, that's the whole idea of a piston to start with, it's going to move downwards and we're going to end up with something like this, right? Let me get rid of these. All right, cool. So that's what's happening as we're going from state 1 to state number 2. And then the question is my heat leaving or entering my system? How much heat is entering or leaving? And then what's the final temperature? We know the pressure over here on this side here is 5 bar or 500 kilopascals. And we also know that the temperature is 300 Kelvin, so 300 Kelvin. All right, so we are sure that the pressure here is greater than 500, right? And I believe the pressure, the temperature will also be higher. But let's check what's going on here. I'm just going to draw the internal energy here on this y-axis, or just leave it as energy, right? So just leave it as energy to simplify things. And then I have state 1 down here, and what we're doing is we are increasing our internal energy to state 2. So we're going upwards in the energy scale, right? And we also know that we're going upwards in the energy scale, and we're putting some work into the system, right? Some work, and we know exactly how much work that is. That is, what is it? 150 kilojoules, right? 100. So we're putting 150 kilojoules in. Okay, so my question to you is, if we are increasing by 80 and we're giving 150, does heat need to enter my system or leave my system? So in other words, we are given 150 to my system, out of which 80 are being used for the internal energy to increase, right? So that means that 70 kilojoules will have to either enter or leave as heat. And how do we figure that out? Well, if I'm given 150 and 80 is being used to increase then the other 70, if I give to my system, then we have a problem, right? Because then this means that effectively I would have the internal energy have to increase by 220, right? The 150 plus the 70. But we know it's only 80, so it cannot be entering my system. It has to leave my system. 100% sure about that, right? We're 100% sure that it needs to be leaving my system. So that is already part of my answer, right? What's happening is heat is leaving my system. It is not entering my system, all right? How much heat? Well, 70, exactly. How? And I can calculate that if I want to do, call it the mathematical way or the strict way. There's a better word for this. Will just be my first law, and we'll have it like so, and I'll say, okay, this is 80 and this is 150, so therefore Q will just be my 80 minus my 150, which gives me minus 70, all in the same units of kilojoules. So what does this negative mean? It means it's leaving my system, and the 70 is obviously the quantity. So this is the first answer to the problem. We have 70 kilojoules and they are leaving my system. All right, so we can write it like such, or you can say 70 kilojoules of heat leaving. Okay, same thing. If you write it like this, your professor understands, you know what's going on. If you write it like this, he or she also understands what's going on. All right, second part. What is the temperature, the final temperature, right? So we know initial temperature is 300 Kelvin. And we also know that the C sub V is defined as the change of internal energy in respect to the temperature in a constant volume process. So what I can do here is say, okay, so therefore C sub V times my change in temperature will be my change in internal energy. And I then can integrate on both sides. And then I'm going to go from U1 to U2, that's delta U. And over here, I'm going to go from T1 to T2. Note that T2 is exactly what I'm looking for. And now here, and I always talk about this, if you've seen the previous videos in the channel, you know this, C sub V does change with temperature, right? So this integration is not trivial. But you note that from the problem statement in the beginning, they're saying, take CV to be a single number. Take your C sub V to be this single number. So therefore, we can consider it to be constant, though we know it's not, right? It's the simplification, and just use a 0.312, right? So what I'll do is effectively, let me do this. Effectively, what I'm doing is grabbing this guy, saying it's constant, therefore it can come out of the integral, and what I end up by doing this integral is C sub V delta T, right? T2 minus T1. And close the parenthesis, and over here U2 minus U1, which is delta U. Right, delta U we happen to know, this we happen to know, and this we happen to know. So the only unknown here is the temperature, right? So I can do, so therefore T2, which is what I'm looking for, minus 300 Kelvin will be equal to 80 kilojoules divided by 0.312. Right, so as long as my units turn out to be right, this should not be a problem. So this is kilojoules, and this is kilojoules per kilograms Kelvin. And we see there is a problem indeed, right? So kilojoules and kilojoules, and we're left with kilograms per Kelvin, which is not what we want. We want just Kelvin because we want a temperature, right? So there is a problem here, and the problem is we're missing the mass component of this guy here. And we happen to know the mass component because it's 2 kilograms. It's set in the problem statement. So I need to include here the mass component, and I need to include it on the bottom dividing so that I can get rid of that kilogram. Oops, 1/2. And we know it's 2 kilograms, right? So I'm putting 2 kilograms here so that I can get rid of this guy here. Okay? So this turns out to be 128.2. Right, so that means that T2 minus 300 Kelvin is 128.2, and this is Kelvin, as we can see from the unit that's left. Right, it's dividing the division, so it's going here to the numerator, right? And therefore T, or T2, we should say final temperature. T2 is 428 8.2 Kelvin. And that will be our answer right there. Okay, so I want you to know a couple of things. Well, we finished the problem, that's it. But remember in the beginning when we saw that this was happening? We had this situation, we were compressing it, and I said, oh, our pressure is increasing for sure, right? Now let's check the temperature. What's happening? The energy is coming from work, right, being applied to my system. And this energy is being absorbed by the gas. That's why the internal energy of the gas increases. As the internal energy of the gas increases, so does the pressure and the temperature, right? They're actually related. Okay, and note that, and this is super important, and it gets super confusing for a lot of students. Note that the heat is leaving my system, and in spite of heat leaving my system, the temperature of the gas is increasing. So it's often that students confuse the fact that heat leaving the system needs to imply that the temperature is decreasing, right? It does not, right? The temperature is related to internal energy of the gas, okay? And the heat that's leaving is actually related to that excess of energy coming from the work. Okay, so this is important for, in a simple problem like this, it's important to, internalize these concepts so that you're firm on these and you're not, in doubt when more complicated problems show along later on. Okay, so as per usual, if you have any questions, just leave them down below in the comment section. And if this video has helped you out, consider giving it a like, and we'll talk soon.